And thanks for the kind invitation to present our work here on the Terrestrial Systems Modelling Platform. And of course, I want to acknowledge my co-authors. And I think the list is definitely not exhaustive here, but so there are many people who have been contributing to this over many years. And this is I feel this is a very fruitful and very constructive development we have been doing. So before I start, I just want to really quickly put out there what the current trends are in ESM. And I think one of the major trends we are observing now is really the increase in resolution to kilometer scale resolution. And this is the expectation here is really that by doing this, we actually are able to resolve more also weather generating processes, and that we are actually able to reduce major biases that we are observing in global scale Earth system models and also in regional scale Earth system models. So, and of course, I mean, it's not only that if you can't do anything, you actually increase resolution. No, if you do that, many things change. So the physics of the atmospheric models change completely. The physics of the let's say feedback models change completely. So we have to resolve more and more biogeophysical and also biogeochemical processes related, for example, to the carbon and nitrogen and phosphorus cycles or the nutrient cycles. We have to include much better physics related to, for example, ice sheets. We have to improve the hydrology. For example, we have to include groundwater in our simulations. And of course, also we have to include the humans in our simulations for human interventions. One example would be pumping and irrigation, which I get to this also in the later slides. And another thing we need, of course, is a more interactive approach to our data with the end user. One concept that has been discussed lately and implemented is these are the data lakes and in connection also with AI technologies, but I will not talk about this here. So so the content really what I want to cover here is I would give maybe a more hydrogeologist perspective on Earth system and terrestrial systems modeling. And in that context, I will talk about in more detail about the technologies we are developing, in particular the Terrestrial Earth Systems Modeling Platform. And then I will provide some applications with a focus on water feedbacks, including groundwater, which might be of interest to you, and I hope to get some questions from you. So you all have seen this cartoon previously, and I will not go into detail here. I just want to actually provide I want to focus on some major processes that are relevant here. So what we have is we have advection of moisture onto the continent with ensuing precipitation. And what we observe over the continent, if we integrate the water balance over a large space and time scale, we see that actually precipitation generally exceeds evapotranspiration on the continent. That means really that the continents are a sink for atmospheric water, and this actually holds also for very arid systems. So the continent actually has to get rid of excess water from the recharge areas like the mountains towards the ultimate sink that is the oceans. And this happens really along these major continental river corridors where we actually have convergence of groundwater towards the major river systems that are then draining the water towards the oceans. And so it's very important to understand here that in that process, actually surface runoff is minor. Actually, the vast majority of the water is drained by our groundwater and base flow towards these river corridors. And this kind of, let's say, dynamics maintains a very delicate water equilibrium on the continent, as I mentioned, from the source areas to the sink areas. And of course, we know that this kind of equilibrium is changing quite a bit. Why? Because we have regime changes in the recharge areas with respect to snow ice processes and the precipitation and also evapotranspiration. And then, of course, we also have a lot of human interventions related to agriculture or other industrial water users. And so you could think about this, that we actually superpose like an anthropogenic water cycle on top of the natural water cycle. That is maybe even accelerating the natural cycle. Okay, so let's look at some of the timescales we have to consider if we want to treat the system holistically. What you see here are fluxes, storages from groundwater across surface water, soil water to the atmosphere. And what you see here is, for example, that there's that groundwater fluxes averaged globally, whatever that means. It's just to make the case here, are fairly small. So it's more than an order of magnitude smaller than, for example, the atmospheric water fluxes. Why? Because, well, atmospheric water is highly dynamic because storage is very small. So the atmosphere can store only very little water. And that is a contrast, for example, to groundwater, where we have large storages on the continent that are also mobilized, for example, by a human use. And that results actually in a very wide distribution of residence times of water molecules in the system. If you look, for example, into the atmosphere, well, we have, a few days or maybe 10 days, a little bit more maybe, that a water molecule can reside in the atmosphere before it's rained out. In contrast, in groundwater, we have a very large mean residence time of maybe thousands of years, and with a very strong tailing towards the very large residence times. But of course, we also have very small residence times, for example, of water along river corridors, where water is actually moved to the rivers very quickly. So, and if you want to treat the system in a continuum way, you have to account for these types of timescales. And on top, of course, these are related then simultaneously also to space scales. So this is one of the major challenges we are facing. So to get maybe towards, the modeling aspects, of that system, we can actually look at that in a more schematic way, in a simplified schematic way, which is depicted here. Where we have basically advection, as I mentioned, from the ocean onto the continent. We have precipitation. Of course, the system is forced on top with radiation. We have evapotranspiration. Then we have now some recharge maybe because of precipitation minus evapotranspiration. We have storage changes in the subsurface, groundwater recharge, base load to surface water, and then continental runoff. So this is a very, very simplified figure, but I'm using this here to make the case of the system, really, of the continuum system coupled from groundwater to the atmosphere. So we can cast that system in balance equations, and we have seen these, of course. We can do this for the atmosphere. We have atmospheric water storage. We have the divergence of so the transport of atmospheric moisture. We have precipitation, in this case, as a sink. Evapotranspiration as a source at the land surface, right? So this is the basic water balance equation. And we know that we can actually integrate this over relatively short time scales. And what happens then is actually the storage term drops out. Why? Because, well, water can store only very little water. The atmosphere can store only very little water. So the storage changes average out quite quickly. And then what is left really is that the transport equals the sink source terms, the precipitation, and the evapotranspiration, which is actually, as I mentioned before, this is the continental sink for atmospheric water. Now, if you come from the bottom up, we can write the terrestrial water budget, where we have the storage change with time. We have precipitation, in this case, as a source, evapotranspiration as a sink. We have continental runoff, and I'm including here also, let's say, the subsurface water divergence, for example, also along the continental margins for completeness. Here in this case, we have to keep this storage term because, as we saw before, the dynamics are much slower, and this term does not average out quickly, right? So what we see already, we can actually combine these two budgets or balance equations via the sink source terms, via this continental sink term. And what we end up with is a unified balance equation from the bedrock, so to speak, to the top of the atmosphere, where the continental water storage equals the atmospheric transport minus the continental discharge to the ocean, to the ultimate sink, the ocean, and then also the divergence of groundwater, for example, also crossing the ocean continent boundary along the continental shelves. Right, and so this quite simple equation really holds, for natural systems over very large areas and large spatial scales. But all these interactions of the system, all these feedbacks, and the nonlinearity is hidden in these simple variables here and these divergence terms. And this is really the crux of the matter. How do we actually resolve these terms mathematically and in simulations? So, but then what happens now if we, for example, include also the human being, right? I mean, so if we include the human being, for example, here with pumping and irrigation, where we have an additional sink term, an additional source term, they might be even equal because we apply it right there on the spot on a farm. And of course, we're going to change, for example, AT, and we would expect that AT will change, will increase actually, right? That's why we irrigate. But what happens now to runoff to the oceans, along the river corridors? Does it increase or decrease? That is not so simple. Why? Because we don't know if precipitation stays the same or is changed by this additional water source. And then what happens, for example, to recharge or the atmospheric transport, and then later even to groundwater recharge. So now with human interventions, the system becomes even more complex. And we have to take that into account in our consideration in our equations. I add that here, as I said here, these sink and source terms. They will induce actually increments, for example, in the groundwater divergence, the runoff, the ET, and precipitation. And this, of course, will then feed back also with the atmospheric transport and will change actually the continental sink for atmospheric water. And this can also be expressed now in this coupled balance equation again. So, but how that really works, this is extremely difficult. We would need really to resolve all these different terms of different space and time scales. And this is our major challenge. Okay, so how do we do this? Our attempt in treating the system as a water continuum, coupled also to the energy balance equations and also to the nutrient balance equations, we try to cast the system in mathematical equations, which are provided here. These are not complete here. And we do this for solving the coupled equation for momentum, energy, and also water for the atmosphere, the land surface, and also for the subsurface. And we're trying to do this with different components models, and how we combine these different component models, I will get to in a second. So this is depicted here. We do this in our Terrestrial Systems Modelling Platform, TSMP, where we have different component models for the atmosphere, as I mentioned before. This is the weather prediction system, or the former weather prediction system COSMO, or the current one ICON of the German Weather Service. For the land surface simulations, we use the community land model from NCAR, or our in-house version of this model, ECLM. And for the hydrogeology and the surface water hydrology, we use our surface-subsurface hydrologic model, PARFLOW. And we'll get to PARFLOW in more detail in the upcoming slides. We couple these component models via an external coupling technologies from our French colleagues, OASIS 3 MCT. And another aspect I want to mention explicitly is really that we also merge our, let's say, physical models with observations via data assimilation technologies. I will not talk about this here today. So these models are computationally expensive, and since we want to apply these over very large space and time scales with high spatial and also temporal resolution, we are really investing a lot in the performance of this model with respect to parallel computing, using different parallel paradigms, and also making sure that these models are performance portable, so we can put them on different architectures, supercomputing architectures that are becoming more and more heterogeneous. And here we use really the multiple program, multiple data paradigm on different hardwares, which I will not go into detail too much today. So you see this on the right here. So this coupling concept again, we have, as I said, icon Cosmo for the atmosphere, which is passing atmospheric variables via OASIS MCT to our land surface model ECLM. In turn, ECLM passes information back to icon or Cosmo related to the energy and water fluxes, also gas fluxes, and then we couple to path flow. Again, via OASIS MCT, here we pass the sink and source terms, for example, root water uptake and infiltration to path flow. Path flow then takes that information and calculates in 3D variably saturated groundwater flow and surface water flow and redistribute this moisture and gives that information back then to ECLM. The system is really modular, which is really nice. So what you can do is you can kind of, well, you can turn off, let's say, remove the atmospheric model from TSMP for TSMP, and you can perform more classic, let's say, hydrologic offline simulations where you force ECLM and path flow with atmospheric time series, for example, temperature, precipitation, and so on. On the other hand, you can also perform more classic, let's say, atmospheric simulations where you use the land surface model only as a lower boundary condition and treat the subsurface in a very simplified way, for example, via free drainage. So this is all possible, or you can also use the different component models individually. So the system is developed in an open way. So we make TSMP publicly available on GitHub. The ownership is with us. So this is with Simulation and Data Lab Terrestrial Systems and the Center for High Performance Computing and Terrestrial Systems. The component models that are part of our system are also available on GitHub in case of PathFlow. If you want to use Cosmo or CLM, they are available on request. These are third-party software. ECLM is also available on our GitHub system, and Icon is also available via another GitHub from Max Planck Institute Hamburg and also DWD. And what we do is here we support applications with test cases that are also available on public servers. And we have a current release, version 1.4, and we are working on a new release where we include Icon and ECLM with new interfaces. Yeah, and you can contact us in case you're interested in using the system. So just quickly to the more details to the coupling. As I mentioned, we have the external coupler OASIS MCT, which governs the overall execution. What OASIS really does, it creates a world communication using MPI, but then passes local communicators to the different component models and a coupling communicator for subsetting the processes, on different parts of the supercomputers. So OASIS MCT, as the name already says, relies on the MCT model coupling toolkit, which has an MPI that provides model interoperability. There's a very useful domain decomposition component of MCT. And also this allows parallel data transfer, which makes the coupling extremely efficient also for large problem sizes. Okay, how does it work in terms of time stepping and the coupling time step between the different models? So you can use different time steps for the different component models. For example, Icon, of course, runs on a very high temporal resolution. Maybe PathFlow you want to run on a coarser resolution because of the slower dynamics. So what's happening is in one coupling time step, Cosmo and Icon and PathFlow are sending coupling fields to the land surface model here depicted as the community land model CLM. And while Cosmo or Icon and PowerFlow are idling, CLM is actually calculating the land surface, water, and energy balances. Then CLM sends the coupling fields back to Cosmo and PowerFlow, and then the atmospheric models, Cosmo, Icon, and PowerFlow are running simultaneously while the land surface model is idling. So this is kind of an asynchronous coupling, and it's very helpful because the most expensive models are running simultaneously, which makes the simulations much more efficient. So now, since I mentioned before, I want to provide the hydrogeologist perspectives. I will talk a little bit more about PowerFlow, our 3D vertically saturated subsurface surface water flow code. This is an open source development with colleagues in the United States from Arizona University, the Lawrence Livermore National Laboratory, or also Princeton University. What PowerFlow also has, it has an integrated land surface model, so an older version of the community land model. And we have also additional versions with, for example, pyroreactive transport or energy transport, and also a version with adaptive mesh refinement. And as I mentioned also before, this model is really optimized for massively parallel supercomputers. So it's a cell-centered finite difference, finite volume scheme with implicit time integration, and it has a very sophisticated nonlinear solver technologies implemented. And what's really interesting also for these large-scale, high-resolution application, it is performance portable and has a heterogeneous parallelism implemented based on the message passing interface and different accelerator architectures. We achieve a very high degree on performance portability because of an embedded like performance portability layer, but I will not go into detail here. If you're interested in this, please contact me offline. What's also important to understand is that we are, of course, also part of the current AI development. So there are PowerFlow emulators available. I can point you to the respective literature, or we can also point you to our developments. Okay, what's very interesting is that what's really neat with PowerFlow is that you can apply this model at various level of complexity. So you can make it a very simple lump model, or you can go all the way down to this 3D variably saturated implementation, also integrated with surface flow. So this really lends itself for hypothesis testing. So if you really want to understand how hydrology impacts the land surface energy balance and also the atmosphere. So how does it look like if you work with PowerFlow? So what we do is, for example, here we initialize the system with an arbitrary initial condition, and then actually we drive the system on PowerFlow with atmospheric forcing or run it dynamically with the atmosphere. And oops, okay, this movie is not working. That's unfortunate. What we would see here is really that the river corridors are developing and actually following like a dynamic water equilibrium on the continent. Of course, the model is very input intensive. So we require different information on, for example, the terrain. We require land cover information, soil cover information, hydrologic information, and so on and so on. And of course, this is a big challenge. Why? Because all these data sets are highly uncertain. They are multi-scale in time and space. And of course, we never have enough data, especially with respect to the subsurface. This is due to this extreme heterogeneity of the natural system. Another aspect that is really a big challenge is the large data we are generating. For example, if we perform climate timescale simulations on the order of 10-kilometer resolution in space, we end up with terabytes to petabytes of data. And of course, this data needs to be analyzed and also visualized. So now we get to some applications here. And of course, the first thing you want to do with these models, you want to test them also against observations. And since I want to give a little bit the hydrogeologist perspective or the groundwater modeling perspective, we are interested in the total subsurface water storage anomalies. And there, one option is, for example, to compare to GRACE, the gravity mission, where you are able to estimate groundwater storage changes on relatively coarse resolution of 400 by 400 kilometers everywhere, globally. And what you see here is a time series of these water anomalies, water storage anomalies over mid-Europe. And so here, the black curve is actually the data from the satellites, including also the reconstruction before 2002. Then you see here our TSMP simulations in blue and green. And if you include, for example, also snow, you actually see that we follow the satellite data really closely. So we are really able to simulate let's say, the longer term trends. Like you see here, there are some trends, on the order of years to a decade. And we are also able to, for example, here simulate the extreme drought of 2018, which is very encouraging, actually. So one question that was posed to us at that point in time was, well, it's great that we are actually able to simulate the past. But in 2018, the question was really what happens in 2019 and 2020, because this drought in many regions of Central Europe was really pretty much unprecedented. And so the challenge here is really, if you go into drought prediction, that at the interannual time scale, the precipitation forecasts are not at all skillful. But this is, of course, key in understanding how drought works, on longer timescales. So our assumption was, at that point in time, we said, well, because we have actually an explicit representation of groundwater in our modeling tools, we are actually able to simulate these long time scale memory effects, and that those will provide actual skill also at the interannual time scale. So the idea was then to actually take into account the atmospheric uncertainty, of seasonal forecasts by simulating an ensemble. And how did we set up the ensemble? Well, we used the last day of the water year of 2018, in this case, August 31st. And then actually we took the atmospheric information from all previous years and simulated the following year with all the atmospheres from the climatology to account for, let's say, the complete atmospheric uncertainty. And this produced actually a probabilistic forecast covering the, in quotation marks, full uncertainty range. And that's what you see here, the result. This is our historic simulation. We end up here in 2018. We initialize our model, and then we take the atmospheric information and we simulate, the following year based on our uncertain atmosphere. And you see here the spaghetti plot, where you see this large uncertainty, but what you realize is actually because of this memory effect of groundwater storage, you see that there is a very high probability that you end up with another dry year just because of this long-term slow dynamic memory, groundwater memory in the system, even for quite moist precipitation ensemble members. And what we also plot here is the trajectory. We called it the current trajectory at that point, which we reconstructed then from the real year 2019 from ERA. So actually, in this case, we actually did pretty well. Okay. So then we were asking, well, if we have this memory effect in groundwater, is there actually also feedback with the atmosphere, with this kind of, this strong water deficit over large areas of the continent? So there we took an approach where we simulated all years of the climatology with the drought initial condition of 2018, where we initialized this also a drought from 2018. So I depict these variables basically with variable in 2018. And what we did then, actually, we calculated the increments of this ensemble were initialized with the drought water initial conditions, and we calculate the increments with the original climatology. So, and then the idea is here really, if these increments are systematic, then actually the drought initial condition has really effect on the variable. And we looked at different variables and, for example, also precipitation, which I don't show here. And we saw, for example, in precipitation that the increments are not systematic. But what's very interesting, if you look, for example, in the cloud ceiling height here, and we see this increment expressed in standard deviation of this variable, we see for the spring of the following year and the summer of the following year, actually, we see a very systematic increment that the cloud ceiling heights were systematically larger based on this previous drought. We also saw that with the lifting condensation level, where we actually found that we had a systematic increase in the spring and the summer, and the same is true actually for the total cloud water content, where we had actually a decrease. And what that meant is that this feedback from groundwater to the atmosphere was positive by an increase in solar radiation, because total cloud water content or cloud cover was decreased. And this actually then fed back also to the drought in 2019. Okay, next application I want to go into is TSMP, applied in the coupled regional climate modeling ensemble of the Kollet project of the World Climate Research Program. In this case, with the CMIP6 forcing. This is something that this is work that is done by my colleague Klaus Gergen. So what we do here is we apply TSMP over the Kollet domain at about 12 kilometer resolution. You see that here on the right. Here, actually, you see also the hydrogeology we implemented in the model. And then we perform the Codex protocol historic simulation and the scenario simulations, in this case, SSP 126 and SSP 370. Note, in this case here, in our simulation, we do not have anthropogenic water use in there and no transient land use change. But what is important for us is that we have a consistent, let's say, initial condition in 1950 based on a very long-term decadal spin-up we were performing. Okay. So now what you see here is you see the mean total subsurface storage anomalies with respect to the historic mean from 1971 to 2000. So here you see in black the historic part of the simulation, and then you see the projection for SSP 126 and SSP 370. And you see this for the prudence region mid Europe, and you see this for the prudence region Scandinavia. And what you see is actually for both scenarios, the total subsurface water storage anomaly is not very strong. It follows actually the historic mean. There is a slight increase over Scandinavia, and this is actually consistent also with results from other projections, also offline projections from the large-scale water models. But what is really striking is if you go further south and you look at the prudence regions of the Iberian Peninsula and the Mediterranean regions, you see actually that especially for this SSP 370, you see these huge drops in total subsurface water storage, including groundwater. In some parts, they seem to be even almost catastrophic. We have to analyze this further if these are related to major drought events. You see this for the Iberian Peninsula and Mediterranean region, and And this means actually that in these regions, the water equilibrium in these parts of the continent is changing completely. What this also means is actually that that it does really matter on which trajectory or which emission trajectory you're really moving in terms of CO2 emissions. If you stay on the SSP 126 or the SSP 370, it really will matter in these regions with respect to freshwater supply. So, and this is a message, I think this is really important. It's also interesting to look at projections of surface water storage changes. We can separate this very nicely in the simulations. You see this here on the left side for the historic simulations. Over Europe, you see very nicely the river corridors that develop naturally in the models. And then you see here the changes, so the increments of the projections with respect to the historic simulation in case of SSP 126 and SSP 370. And I think what is important here to realize, you see again this kind of gradient from north to south, but you see that there is kind of a fine line, right, along a latitude belt. And I think it's very important in future to figure out how uncertain the position of this latitude belt line really is. Where it really sits, because this will have huge implications also for future water resources in Central Europe. Okay, I will want to quickly mention that we use our modeling tools also for simulations and outreach for different water sectors over Central Europe. This is an example from Alexander Benaflam and colleagues, where they implemented a extremely high resolution integrated model of power flow and CLM over Central Europe. Here we really, you see really all the details that you achieve at that resolution, where you can really follow all the different river networks. You can resolve the variability across orders of magnitude, also related to land use. And I think this is really key if you want to provide actionable information, for example, to farmers. And that's what we do in this adapter project led by Klaus Görgen. So we use this information, as I mentioned, for knowledge transfer. We have a website here, which we call the Wassermonitor, the water monitor over Germany, where we provide information on a daily basis at the weather time scale on the order of 10 days. So these are forecasts. We provide all the essential water variables. And another aspect we are doing also are 4 times or every quarter year, we perform a seasonal forecast with ECMWF 52 member ensemble. And we publish this also, and including also, let's say, uncertainty estimates at the let's say the community level. Okay, where do we go from here? So based on our technical developments, we are now able to scale this up from the continental scale to the global scale. So we are now able to perform global groundwater modeling at 1 kilometer resolution with power flow. So these are really continuum simulations from the deeper subsurface, 60 meter to the land surface in 3D. We inform this model with global hydrogeology and soil information. Of course, as I said, we never have enough data, so there is very large uncertainty in these simulations. I see these simulations currently really as proof of concept studies. And we are now performing a spin-up towards a steady state with effective recharge. So as I mentioned, these types of models are really computationally expensive. We run this currently on 320 NVIDIA GPUs, but we can achieve with these effective recharge forcing, we can achieve 1 year of simulation on the order of 24 hours wall clock. Yeah, I just want to give you a quick idea on the input data. This is here, for example, the hydrogeology based on CLIMS. As I said, this is really relatively coarse information, but I think we have a high potential really to at least regionally implement much more detail, in future. So I think this is really a work in progress, and we try to also do this in a community approach. Yeah, so if you do this, you really achieve, you really resolve variability over 4 to 5 orders of magnitude in space. So you achieve really extremely high detail in the simulation that allows you to interrogate what happens locally in watersheds. And since these simulations are consistent, physically consistent, we feel that the results will enable comparability across different continents and also transferability of results and findings. Yeah, so you can zoom in here and yeah, so this is really actually at one point it's a problem to plot these results at native resolution. Another aspect that is done by Jan Weinkammer in a big project, in a big system modeling project in Germany. He is also implementing path flow or running path flow at the global scale, coupled to ICON. Here, this shows you a snapshot, for example, of path flow nested in a global ICON run over Europe. And there we are now able to interrogate also feedbacks with global circulation patterns beyond, let's say, the regional climate scale. And one of the next steps here is really to also perform latitude belt simulations and also perform, let's say, simulations with path flow also fully on the global scale. Okay, what are the conclusions? Groundwater is indeed an important part of the Earth system's water continuum. I hope we can show this. So the hydrogeologist's perspective, kilometer scale prognostic groundwater flow simulations are possible, really from the regional scale to in our opinion, to the global scale, with all the obvious and not so obvious limitations. And we feel that these results really provide a new level of physical consistency and realism. And we feel that this is really key in feedback simulations in Earth system models, and especially if you go to, for example, climate time scale or beyond. We are aware the data challenge is really ubiquitous, but we feel that this will never go away. So we will never have enough data to inform our models and to really beat all the uncertainties. But this is not a reason not to do it. In the exascale realm, ultimately, when you move now to the new machines we have in Jülich to Jupiter, we will be able, actually, we have to transition to even higher resolution, to 10 to 100 meter resolution globally. And yes, so bottom line, in our opinion, hydrogeology, groundwater flow modeling is important in Earth system modeling. And I want to shout out to the community. We have been setting up a global groundwater network in GBEX. And I would like to reach out to the community to participate in this, because we really think that it's important to inject physically consistent groundwater modeling into our system modeling. And this is it from my side, and I'm happy to answer any questions.